Physics, Lecture 3, Work and Energy. What is energy? Energy, put simply, is a system's ability to do work, otherwise make something happen, the units for which are in joules. There are two types of energy that we will be discussing. The first is kinetic energy. This is the energy of motion, and it's represented by the equation K equals 1/2 mv squared, or kinetic energy equals 1/2 mass times the speed squared. Make sure you realize that kinetic energy is related to speed, not velocity. This is because energy as a whole does not require a vector quantity. The other type of energy is potential energy. This is the energy associated with an object's position in space. It could also be related to intrinsic qualities of a system. Potential energy can come in multiple forms. The one that we're going to go over in this one is gravitational potential energy and elastic potential energy. However, there are such things as chemical potential energy. If you recall from your biology classes, in biological systems, this chemical potential energy is largely derived from ATP in living organisms. That'll be for a different day though. Today, let's talk about the other two. Gravitational potential energy depends on an object's positions in reference to some level. For example, if I were to hold a ball in the air, if I were to drop that ball, it would have a certain potential, and it would switch to kinetic energy as the ball fell. But while it's dangling in my hand in the air, it only has potential energy. This energy is represented by the equation U equals mgh, or potential energy equals mass times gravity times height. Elastic potential energy, on the other hand, is the potential energy stored in elastic systems, most commonly in a spring. When a spring stretches or is at rest, it has a certain energy that converts and fluctuates between potential and kinetic. This equation is represented by U equals 1/2 kx squared, with x being the position of the spring and k being the spring constant. You'll realize that this looks an awful lot like kinetic energy. When you're talking about the total mechanical energy of a system, you're looking at the sum of an object's potential and kinetic energies, or E equals U plus K. This is a direct representation of the first law of thermodynamics, which addresses the conservation of mechanical energy. To put it simply, it states that energy can be neither created nor destroyed. Energy is merely a transformation or a transfer from one form to another. When it comes to the conservation of mechanical energy, we discuss this in terms of two different types of forces, conservative and non-conservative. Conservative forces are path independent. They do not dissipate energy. This is the most common two on the MCAT, gravitational and electrostatic. Below is the equation. Put simply, it states that the change in energy is the change in potential and the change in kinetic, which has to equal 0. Path independent means that no matter how I get from the beginning to the end, it doesn't matter what path I take. The change in energy will be the same. Non-conservative forces, on the other hand, are where the mechanical energy total is not conserved. Examples are friction, air resistance, and viscous drag. Basically, energy dissipates from the system. In general, the work done by these non-conservative forces will equal the amount of energy that is lost from the system. Now that we've discussed energy, let's talk about work and what it means. First and foremost, let's talk about force and displacement. When something exerts a force on or against something else, it does have a work, and this is represented by work equals force times distance, or work equals force times distance cosine theta in reference to an incline. Below is a picture of Sisyphus, a Greek man who was cursed by Zeus to roll a stone up a hill infinitely over his entire eternity. Now, obviously, studying for the MCAT is not a Sisyphean task, but it is a good representation of work in terms of distance. Now note, with the cosine, you do have to use trig identities. You remember this from the previous lecture, but let's have a quick recap. Force times distance cosine theta. So we have a force applied on the object, a distance, and cosine theta is to get it into our horizontal coordinate. Another type of work is that done by pressure and volume. The work on these is calculated by looking at the area under the curve of a PV graph. For the sake of the MCAT, you will need to know how to read these, and this is something we'll go into in our next module. There are two types of processes in the pressure-volume curve that you need to understand. The first is isovolumetric, or isochoric processes. As the name suggests, these are processes that have constant volume. Isobaric processes, on the other hand, have a constant pressure. For isobaric processes, you can calculate the work by looking at the pressure times the change in volume. Let's draw a couple of these out and have a closer look. If I were to draw a PV graph, pressure and volume, and I were to draw it looking like so. I have a P1 and a P2. Just by looking at this graph, what type of process do you think this is? If you guessed isovolumetric, you would be correct. As you can see, even though there's a change in pressure, there's no change in volume. What is the consequence of this, however? Well, there is no area under this curve. Therefore, there is no work done by this system. In another example, what if you had a system that looked like this? What type of process would this be? That's exactly right. This would be an isobaric process. As you can see, the pressure is constant. What you do note, though, is that there is an area under this curve, which means that there is, in fact, work being done. Now note, not all PV graphs are going to have such nice isovolumetric or isobaric processes. Sometimes you're going to get an amalgamation of the two. Here's an example of that. So if I were to have a process like so, I would simply just have to calculate the area underneath. If you wanted to get really detailed with it, you would just calculate this top bit using the area of a triangle, and then this bottom bit using the area of a square or rectangle. For the sake of the MCAT, it would be helpful to know how to do this, but more importantly, it's better if you understand what these things are representing. Also note that the names of these processes will give away a lot of what they are. Power is the rate at which energy is transferred from one system to another. It's, put simply, work over time. Now, why would we want to know work over time? Well, keep in mind, work is not just another form of energy. Work is a process, and power is a way to measure this process over a given duration. The SI unit for power is the watt, and the equation is listed below. Power is simply work over time, or the change in energy over time. The work energy theorem. This simply states that the net work is equal to the change in the object's kinetic energy, which is listed below. It's simply the final kinetic energy minus the initial kinetic energy. This is very powerful in a sense that you can calculate work by simply looking at the energy of the object. Finally, mechanical advantage. This is the last subject for this lecture. For the sake of the MCAT, you will be discussing simple machines, which are machines designed to provide mechanical advantage. Examples are listed to the right. Note that for the MCAT, you will pretty much always be tested on one of these examples. When you're discussing mechanical advantage, you have to discuss efficiency as well. Both of these relations are simply what you get out versus what you get in, what you put in. Mechanical advantage is the ratio of the force applied versus the force that you exert. Something that is very advantageous, obviously, will have more output for less input. The same can be said for efficiency. If you're running at perfect efficiency, then everything that you put in is what you get out. So, for you math geeks, if you figured it, if you have the same work out as the same work in, then you should get an efficiency of 1. Note, an efficiency of 1 is practically impossible. Everything has some level of inefficiency. What you do need to look at, though, is how best to minimize any sort of loss of work, to thus maximize your efficiency. That'll conclude our work and energy lecture. In the next module, we'll go into thermodynamics. We'll see you then.